Welcome back to another video. In this video, we are going to be talking about operations with vectors. Yes, so we talked about vectors in the last video. So this time we're going to talk about performing different operations with vectors. And here I have all the different operations that you can perform, plus one additional that we'll talk about on another slide. But the first one you could do is that you can add two vectors together, okay? Okay, so you can add two vectors together. So if we add vector AB plus CD, basically you add the horizontal components together and you add the vertical components together and you get that equals to A vector A plus C and B plus D. All right, so this is your new horizontal component. This is your new vertical component. You can also take a vector and multiply it by a scalar or a number. And what you do is basically it's like distributing. You multiply both the horizontal component by that value and the vertical component by that value. And so that ends up being Ka, comma, Kb. Now, if vector u is a1, a2, then if you wanted to take the opposite of vector u, basically you just change the signs on both the horizontal and the vertical component. And lastly, if you wanted to subtract two vectors, this will be the same as, it's like distributing that negative n, changing it to plus, and then saying that's negative c and negative d, and then you would combine that. So basically you're just basically doing a minus c and b minus c. It's just showing you how you're turning it to the opposite first, and then you're changing it to the sum of two vectors. So a vector AB minus vector CD ends up being vector A minus C, comma B minus D. All right. So these are all the different operations you can do with vectors. And so we're going to work a few examples. Okay. Okay. For this first example, we want to let u, the vector u, be defined by negative 2, 1, and the vector v be defined by 4, 3. And we want to find the following. We want to find u plus v. And we also want to find negative 2u, okay? So I am going to see if we can first find u plus v. So in order to find u plus v, we will have to add negative 2 plus 4. And we will have to add 1 plus 3. So u plus v would be equal to 2, comma 4. That is how we would define u plus v. All right, so that's part A. For part B, we want to find negative 2u. So that means we're going to do negative 2 times the vector negative 2, 1, which is the same as saying negative 2 times negative 2 and negative 2 times 1, which actually equals 4, negative 2. Oops, not a comma. These little arrow looking heads. So 4, negative 2 would be negative 2u. Okay, now I want you to try this one. U is negative 2, 1, and v is the vector 4, 3. I want you to find 4u minus 3v, okay? 4u minus 3v. Okay, so let's walk through this. 4u minus 3v is equal to 4 times the vector negative 2, 1 minus 3 times the vector 4, 3. 4 times negative 2, 1 would be negative 8, 4. And 3 times 4, 3 would be 12, 9. And if you subtract those, you get negative 8 minus 12 and 4 minus 9. You get the vector defined by the point negative 20, negative 5. Is that what you got? Hopefully that's what you got because that's the correct answer. If you have any questions about that, don't be afraid to put them in the comments below and I will respond. All right, let's keep going. Next, we're going to talk about a unit vector. A unit vector is a vector with a magnitude of 1. And we have two examples of a unit vector over here. This one, this is the vector defined by 0, 1, the point 0, 1. And this is the vector defined by the point 1, 0. So we will write both of those vectors like this. The first one would be 0, 1, and the second one would be 1, 0. So this is the vector j, and this one is the vector I. So those are two unit vectors. Those are two examples of a unit vector because their magnitude is 1. Remember the magnitude, so the magnitude of j would be equal to the square root of 0 squared plus 1 squared, which is equal to 1. And the same thing for I. The magnitude of I would be the square root of 1 squared plus 0 squared, which is also 1. Now, those aren't the only ones, but those are the most obvious ones. And so we can write every vector with an I and a j in it. So if we have a vector v that's defined by AB, then we can write vector v as AI plus bj. So for example, this is vector has defined by the point 3, 4. So that means you go over 3 and up 4. Well, this is 3i, because remember I was from here to here. But if you multiply by 3, this is 3i. And then this vector from here to here was j, but if you multiply it by 4, you get the vector 4j. So this vector u, even though it's defined by 3, 4, so like we will write u like this, 3, 4. U can also be defined as 3i plus 4j right here. So we can also define u by that. So we can write every vector in the form with I and j in it. And this is how you take it and generalize it. So let's look at an example of doing that. Oh, before we do that, we're also going to talk about the dot product. It's like multiplying two vectors. So the dot product of vectors u and v, if u is defined by AB and v is defined by CD, is denoted u dot v, and is given by the following. Is A times C. So you multiply the horizontal components and you multiply the vertical components, but you add those together. So the result ends up being a number and not an actual vector. Alrighty. So that is the dot product of two vectors is the sum of the product of their first components and the product of their second components. So now let's look at some examples. So here's a vector defined by 6, negative 3, and we want to write it in the form of AI plus BJ. Well, that's just simply 6i minus 3j. So you just basically put I with the first component, the horizontal component, and j with the vertical component. And that will be your answer. That's simple. All right. Next one. Find the dot product of 2, 3, vector 2, 3, and vector 4, negative 1. So now the dot product, remember, is the product. So if this is u and this is v, then u dot v will be the product of the horizontal components, so 2 times 4, plus the product of the vertical components, 3 times negative 1. 2 times 4 is 8. 3 times negative 1 is negative 3, so it'll be 8 minus 3, which is equal to 5. So the dot product of these two vectors, u dot v, will be 5. Pretty simple, right? Okay, you try one. You try this one. Find the dot product of the vector 6, 4 and the vector negative 2, 3. Try this and see what you get. All right, did you get 0? If you got 0, then you were correct. You will do 6 times negative 2 plus 4 times 3, which is negative 12 plus 12, which is equal to 0. So the dot product of those two vectors would be 0. Here are some properties of the dot product. So for all vectors u, v, and w, and real numbers k, the following hold true. So this very first property here, it just basically says that the dot product is commutative, meaning you can switch it around and you still get the same thing. So u times v is the same as v times u. The second one says that the distribution property or the distributive property also holds for the dot product. So if you have u dot, the sum of two vectors, then you basically can distribute that u into the v and the w. So u dot, the sum of two vectors v plus u, will be the same as the sum of u dot product with both of those vectors. And it holds true on both sides. So for B, the u was in front of the sum of the two angles, and for C, the w is on the other side of the sum of the two angles. And so that still holds, that distributive property still holds here, okay? And then you have this, similar to the associative property, you have k times u. So you have a scalar vector here. You're taking k, the vector u, and multiplying it by k. And you're doing that dot product with v. Well, this is saying you can move the parentheses around and you still get the same thing. So I could put the parentheses around the u and the v and do dot product uv and put the k on the outside. I still get the same thing. Or I could put the k in with the v and I still get the same thing. This says the 0 vector times any vector is the 0 vector. So just like with the number 0, it's the same thing with a vector. And this says if I do the dot product of a vector with itself, then I get the magnitude of that vector squared. Alrighty. So these are a few properties of the dot product. And then last thing we want to talk about is the geometric interpretation of the dot product. So if you have two vectors u and v, and you have an angle between those vectors, then let's talk about what the dot product actually means. So if we were to create a triangle, we could use the law of cosines, and I'm not going to walk through every step of it, but we could use the law of cosines to solve for that angle theta. When we use the law of cosines, we get to a point in that algebra where u dot v is equal to the magnitude of u times the magnitude of v times the cosine of theta. And this is basically, that part gives us what the dot product means. The dot product of two vectors u and v is equal to the magnitude of each of those, the product of the magnitude of each of those vectors times the cosine of the angle in between those two vectors. All right. But we typically solve this for cosine of theta by dividing both sides by the magnitude. And this is usually what we see, or this is usually what we use in this geometric interpretation. So we end up using cosine of theta is equal to the dot product of u times v divided by the product of the magnitude of both of those. And so we usually use it in this form because we usually want to find the angle between the two vectors u and v. So here's an example of actually doing that. Find the angle between the two vectors 3, 4, and 2, 1. So if I was just to sketch those, vector 3, 4 would look something like this. And vector 2, 1 will look something like this. And this is really small, but basically we want to know what is that angle in between there. Get my laser pen. So what is this angle in between those two vectors right there? That's what we want to know. And so we're going to use that geometric interpretation in order to figure this out. So we know that the cosine of theta, and theta represents the angle in between them, is equal to the dot product of u times v, or uv, divided by the magnitude of u divided by the magnitude of v. So we need to find each of these components. So first we're going to find the dot product of u and v. Well, remember the dot product is the product of the horizontal components added to the product of the vertical components. So 3 times 2 is 6, 4 times 1 is 4, so 6 plus 4 is equal to 10. So the dot product of u and v in this case is 10. The next thing we have to find is the magnitude of u. So the magnitude of u would be equal to the square root of 3 squared, so 3, plus 4 squared. That's the square root of 9 plus 16, which is the square root of 25, which is equal to 5. And then the dot product of v will be the square root of 2 squared plus 1 squared, that's 4 plus 1. That's the square root of 5. So in the denominator here, we get 5 square roots of 5. You can kind of reduce that a little because you see 5 go into both this 5 in the bottom and this 10 in the top. And that becomes 2 over the square root of 5. So you can use that number instead. And if we were going to have to leave that like that, we wouldn't be able to leave the square root in the denominator. So we wouldn't actually leave 2 over square root of 5 like that if that was our final answer, because we can't leave the square root in the denominator. We would have to rationalize the denominator. However, we're not going to leave it like that because we want to solve for theta. And so since we want to solve for theta, then we have to take the inverse cosine of that value. So the inverse cosine of 2 over the square root of 5 is what we actually want to find. So you want to plug that in your calculator. Type in the inverse cosine of 2 divided by the square root of 5. And you should get, let's see, I got 26.565051118 and some more numbers. So theta is approximately, if we round it to 2, or let's just round it to 4 decimal places, we'll say 26.57 degrees. And there are no significant digits given in this number, so it'll have to tell you what to round it to. So the angle between those two vectors would be 26.57 degrees. So that's how you would use that geometric interpretation in order of the dot product in order to find the angle between the two vectors. If you have any questions whatsoever about how we work this problem or any of the other problems in this video, again, don't hesitate to put them in the comments. Thank you all for watching. Hopefully this video helped you and it made sense. If it did, go ahead and hit that thumbs up button for me. And I will see you all in the next video.